All right, looks like the login chat room and webinar room is gradually filling up. We'll give it just a couple of minutes and then we'll go ahead and get started. Give it about one more minute, then we'll get started. And as you're logging into the Zoom meeting room, please say hello to us in the chat box and tell us where you're from. We're always interested to know where folks are from. A couple more people joining us. All right. Got some folks from Houston. That's great. All right, it looks like it's leveled off. We'll go ahead and get started. Good morning, good afternoon, good evening, everybody, depending on where you may be logging in from around the world. I am Rob Burgess and I head up business development for Sinobiological. And it is my pleasure and honor to welcome each and every one of you to the next installment in our Lock and Key Immunodetection webinar series, where we hear about cutting edge technologies as they relate to protein and antibody engineering primarily. We have a fantastic speaker today whom I will introduce in just a minute. And the topic today is on AI and its implementation for construct as well as protein engineering. So we have one housekeeping issue, and that is, I ask everybody if you have questions for our speaker, please type them into the chat box. And at the conclusion of the webinar, I will run through the chat box and get to as many questions as possible, hopefully all of them. And like I said, go ahead and say hello in the chat box and tell us all where you're from. We're always very interested to know where people are logging in from around the world. And now it is my pleasure and honor to introduce our speaker for today. Our speaker is Chalar Boskert. Chalar is the co-founder of Orbion, a Berlin-based company building predictive models for protein characterization and construct design, as well as helping scientists to reduce failures at the bench. With a computer science background, he works end-to-end on the problem, building and benchmarking Orbion's machine learning models and designing the experiments that test where those models genuinely help in the lab and where they do not. He works directly with contract research organizations, structural biology, and biotech teams across Europe and the US who put those predictions into production. He is an author on Orbion's preprints and technical reports. And before Orbion, spent a decade building and scaling software companies. And the title of Chalar's talk is Before You Engineer the Protein, Engineer the Construct. And Chalar, it is a pleasure to have you. Welcome, and we will now turn over the webinar meeting room to you.
Thank you very much for the introduction, Rob, and the pleasure is mine. I really appreciate you and Sinobiological team's invite to the Lock and Key webinar. It's a pleasure to be here. So hi, everybody. Thank you for joining the webinar as well. I would like to maybe start with a quick question in your head, actually. So how many times have you pulled a construct from a paper, expressed it, and simply accepted whatever came off the column? So that habit is what I actually want to talk today during the webinar. I'm Chalar, as Rob has introduced, co-founder of Orbion, and we spend our time on the part of the workflow that gets the least attention, the construct, before you ever touch the protein sequence itself. So now let me show you what I mean. So here there are two constructs. So on the top you see construct A, which has a twin strap with a 3C protease on the N terminal, and the folded core of this specific target was preserved. And on the bottom line, you can see the construct B, which has the same folded core and uses the same tag strategy. But as you can see, this time it's flipped and it's used on the C terminal. And on top of that, construct B made a different decision. So when it's designed, the designer, whoever that is, decided to keep 23 disordered native residues on the C terminal. Now, this is a bit of a counterintuitive idea, considering that those residues are very disordered and will be flexible. And when you look at this, which construct do you think would actually win at the bench? To give you maybe more information, this is the disorder map of the protein that we are talking about and the AlphaFold structure. So construct B actually kept the disordered C-tail part significantly more than the construct A, where, as you can see on the screen, the structure from AlphaFold 2, this yellow part that I'm talking about. Now, the results, of course. So construct A produced more purified protein. So when it went through expression and purification, we have seen that construct A led to 2.4 times more purified protein than construct B. And if I'm actually caring about the purified protein amount, then I can immediately say that, okay, construct A is the winner, and that will be the construct that I will probably proceed downstream to. But there is a catch. When we actually characterize in the lab, then we see that construct B wins on three different lanes. It wins on attainable concentration, it wins on polydispersity index, and it wins on the final concentrated material. So if I was actually looking for a construct that would have led to more protein at the end of expression, I would have selected A. But if I were to go with a well-behaved, better behaved construct for anything that I will do downstream, then I should have picked construct B. But when you look at the literature, construct A came out. So if I purely close my eyes and stuck to that, I would have gone with something that would have produced less results. And today we are actually specifically going to do a deep dive on this topic and talk about different angles and how different variables actually affect the construct strategy. And of course, literature gives you a starting construct, but not your entire design space. Now, to quickly introduce what we are doing as Orbion, we are a Berlin-based AI protein research company, and we are providing a machine learning platform to our customers in the biotech labs, where we support them on construct engineering and protein engineering on optimizing for yield, developability, and thermostability. Our platform works and supports scientists on three lanes. First, our machine learning models can characterize those targets, provide them insights on potential post-translation modifications, ligands that this protein may interact with, and give a general information about that protein with regards to how they localize. Then we help them generate and rank different variants for yield, stability, or developability. And then we match them with the wet lab protocols that they can take and start executing, supported by the literature hits. Our platform looks like this. I'm not going to go deep, of course, but simply put, with structures, users can see everything on 3D structural views, evaluate different mutations and how they affect the fold. And as you can see on the right-hand side, can screen through hundreds of construct ideas in a very easy user interface. Now, this is the end of the commercial break. I will proceed. So the first question is, maybe looking back, why did the literature construct become the default? Why are we starting every research campaign by checking what is already published on the literature and started working on it? It has a very simple answer. Expression in the past was extremely expensive. So back in 2000s, per DNA base pair by special arrangement was costing around $12. Now, this was, of course, 26 years ago. Fast forward to today, we see a significant decrease on the cost of that. So creating another construct has become significantly cheaper over the last 26 years. And of course, this affects everything downstream as well, because once expression was the gate, everything happening after purification and seg was being very expensive as well. But now the expression blocker is out of the way, and we can express proteins on a scale in a significantly more affordable budget. We can also run downstream studies faster and cheaper as well. But then comes a problem. The economics have changed, but our high habits did not have enough time to actually adapt into them, which is not a phenomenon that we see just in biotech. This is across all industries. If a technology and the cost that is attached to it improves over time, the teams are having hard time adapting to those situations and change their behaviors. And which is why we are still relying on the literature constructs. But a literature or a published constructs proves feasibility, meaning that they answer just one question. Can this protein be made in a certain way? And then we get an answer to it. But it's not the limit of what's really possible, because considering all the boundaries, all the fusions, all the tags that we can actually use, there are almost endless possibilities that we can evaluate. But most of the time, we just discard them as ideas. But having all these ideas, having all those possibilities, how would we be able to actually manage the toolbox? How would we evaluate what to use, what not to use, and what to do on the experiment that we are designing today? Now, there are four strategies in the toolbox that we can use. And from left to right, they are actually showing how manageable and how much they affect the core of the protein that we are aiming to experiment on. On the left side, there are three strategies that can be used that actually often are reversible and don't risk changing the core of the molecule. These are boundary settings. So how are we going to truncate or discard certain part of the target that we are working on? Which tags we may actually introduce for solubility or for different stabilization or different goals that we have, and the fusion proteins that can be used as helpers to accelerate the process or again enhance solubility or other experimental variables that we are looking into. And there is also this other line that I have specifically used the red color with, which is the mutations. And the reason that it's actually in red is because mutations introduce changes on the sequence, on the protein itself. And why is it red? Because every change in the sequence is introducing a change on this very complex molecule that is really hard to estimate and predict and model how the side effects are going to be. Because mutation rewrites the molecule itself. It's extremely powerful because it has an ability to actually rescue a fold that nothing else can reach. Boundaries or tags can help until a certain setting, but mutation can increase thermostability or can introduce different functional properties that you may be looking for. But the risk, you cannot cleave it off. You cannot undo that. Once it's done, and you can see the results with regards to if it helps or not. And if it doesn't, then what you have will not be usable, and it has a risk of introducing a lot of side effects besides helping with the fold or the thermostability. And another thing about mutations is that it's a very challenging area to work on. Only 9% of the publicly available mutations actually lead to successful stabilizations on the proteins that they were actually applied to. The rest 91% were either didn't have an effect or led to adverse effect on the stability that they were screened for. And another bigger problem is that the stabilization modeling products, for example, the tools that we use to measure if a mutation has a positive or a negative impact, has a ranking power of almost a coin flip. So we cannot really use a computational product that is out there today in a very easy way to screen through the mutation ideas that we may have generated internally. On the other hand, as you can see on the constructs that I have shown in the beginning, as long as we keep the folded core and as long as we use boundaries or different tags, we still may be able to get significant lifts on the yield or on the developability of the molecules that we are working on. And because of that, before selecting which strategy to actually proceed with, we first need to name the problem. Is it about the intrinsic stability? Are we looking for changing the fold and making the protein that we are working on more stable? Or are we looking for higher expression yield, solubility, or better behaved constructs? If it's the first one, then mutation will be to-go strategy, of course. But if it's about the sample, then we have stronger tools that can actually help us significantly without affecting the core and without requiring a big budget to screen through with a risk of failure. But then the question, of course, becomes, can the construct lever be large enough to justify testing for a panel? And this is why we have actually done a test on TNF-alpha. I'm sure a majority of you will have a know-how about this protein, but simply put, it's a homotrimer and it's a cytokine cleaved from a membrane precursor. So it has one transmembrane helix, and then it has a very large soluble domain as we define it as the functional core. And what we have done to test and evaluate the power of construct design is we have designed a panel of 24 different constructs that was looking into two different things in a statistically significant way. The first one is evaluating different domain boundaries. So how much effect the construct starting point will make on the expression yield. And the second axis we looked into was the surroundings of the core. So which fusions or which tags may have a positive or a negative impact on the specific target. And these are the expression yield results that you can see on the screen. This is kind of a challenging chart to actually interpret the results. But simply put, on the left-hand side, you can see the fusions that were used or the fusion combinations. On the bottom, you can see the construct start residue, if it's the full construct without any truncations, or if it introduced any truncations on the N-terminal. And the color coding gives you the yield. So the higher or the stronger the blue is, then higher the yield is as well. And as you can see here, we see significantly higher or darker blue colors on all the constructs that are truncated after the maturation site. And when we look into the start residues specifically with the expression yield shown on the left side, we see that between the lowest and the highest bar, there is around over tenfold difference on the expression yield, purely based on the truncation that was applied on the C-terminal. And that difference between the construct that started at the residue 71 and residue 80 is over 13%, 13 times, not percent. And this difference is purely based on the boundary application strategy and doesn't include any mutations. Which is why I can easily tell that boundaries on this specific target decided the result. So all the truncation that happened before the maturation site led to significantly lower expression yield than the truncations that applied after the maturation site. And all of those kept the core, functional core, so the protein was able to still fold into the homotrimer that it was folding in its natural setting. And with regards to fusions, of course, we have also evaluated them as well. And on this specific target, although our expectation was a positive result, we have seen that no fusion construct has led to more yield than the construct with GB1 expression booster attached. And we have also seen another interesting finding where MBP alone led to significantly higher expression yield than the construct with MBP plus sumo. As a footnote that I would like to mention, on these comparisons, the construct boundaries were the same. So we were able to actually make a direct comparison with regards to the impact of the fusions that we have attached. And in this TNF-alpha panel, the largest yield differences aligned with the starting boundary, as you can see. And what I would like to mention here is that this was a panel of 24 constructs. This number can increase, of course. But as part of this test, we have also seen that this data only becomes useful if we can actually see how they will rank against each other before we go into the bench. So our model that was predicting the ranking for expression yield has actually successfully ranked these constructs against each other based on the real yield that we have seen on the cell-free environment. But as you can see, the wider the design space is, we need better selection rules because this was one transmembrane helix, transmembrane protein on a cell-free environment, but there are different expression hosts that you may be expressing or experimenting with. Mammalian, E. coli, insects, and different systems. And you may be working on different proteins, of course, such as GPCRs, kinases, different soluble targets, different enzymes, and hence we need to know what to look into in order to know how to strategize around the construct. And there I would like to mention actually a couple of the do's and don'ts, or maybe looks and not looks in this list. So what we can actually vary as part of the construct design is the boundaries that we can set, the truncation strategy on the N and C terminals. By knowing how disordered a protein is, based on the expression host that we are running and based on how the membrane topology is, makes a big impact on the result that the construct is going to yield. Signal peptides, of course, play a very important role as well, such as also fusion partners, tech types, and positions, along with the linkers, help us a lot on creating the right structure and getting it ready for an experiment. But what must be respected is the active sites, binding interfaces, PTM sites, and the membrane topology. And why must they be respected? It's because they are the things that are making that protein important or make it work the way that is naturally evolved to be working. So if we have an enzyme and if a construct or construct strategy actually introduces a change that removes some of its functionality, it may not be what we were looking for. And hence, those areas should be the areas that we should avoid when we are designing a construct. And I will come back to the construct, the comparison that I have mentioned in the very beginning of the session. So the construct A, as mentioned, was actually driven from literature. And construct B was designed by our own AI model, which was very confusing and was very scary to us in the beginning as it kept 23 disordered native residues. But our model was very confident that construct B was actually going to have a higher developability potential than construct A. And it also showed that the forecasted or predicted yield was going to lower than construct A, which is what made us slightly more confident to proceed with this construct strategy. And as you can see here, the change in the truncation part and the change in the position of the tagging strategy has affected the expression and the concentrated yield significantly, where it inverted how the results are observed in the lab downstream. But on top of that, we didn't introduce any mutations. We only have changed the tag strategy and the truncation or the domain boundary, which is why we haven't seen a big thermal difference on the lab after the experiment was done. So what it supports is construct choice, moved how the protein behaves in solution. But what it cannot do, which is something that mutations can actually help with, is moving the intrinsic stability of the fold. And a selection rule is not neutral, as mentioned. It decides which biology you get to learn from. So if we selected on yield, then the literature construct would have been the winner in our case. But if we were looking for concentration, then construct B would have been the go-to strategy on the path that we were keeping on. And predicting the expensive readout doesn't just rank your ideas, it lets you also generate better ones. Because what we have seen over and over on different studies is that a lot of gains come from constructs or strategies on unexpected areas where they turn out to be resulting in very positive or strong gains as part of the experimentation process. And as you have seen, there is no single rule where following disorder, following PTMs, or following potential aggregation risky residues, where based on the expression host and based on what you're looking for, they can completely flip. And one thing that can harm on a specific host may actually reward you on another host, which is how we have seen that on FGF21 through keeping disordered residues on the C-terminal, and also have seen on TNF-alpha, which was based on the domain boundaries. And because of that, the first thing to do is to actually decide on the goal before starting the experiment. Of course, a protein is going to be expressed, but we know that expression is not always the goal that one is actually seeking on the bench. If it's, of course, about bulk reagent production, maximizing for total yield will make total sense. But if it's about biophysics monitoring, then concentration would be the key goal here. If it's about crystallography, then lattice compatibility, maybe the metric that you may be optimizing your construct for. But if it's for therapeutic reasons, then stability and low aggregation, maybe the go-to area, where then you may also consider mutation strategies to see how you can actually make the target more stable. And because of that, for the process, we of course first need to look into literature to see what is known about this target, not just for the construct strategy that worked, but also what are the important characterization information that is already available in the public domain. And then we should start creating a panel of constructs and rank them through using computational tools so that we will have a prioritized candidates that we can bring into bench that will give us the maximum amount of learnings, but also will give us or introduce a good chance of improving the yield or optimizing for the metric that we are working on. And then, of course, biology doesn't happen on computer, but it happens on the lab. So we have to measure everything and then change or select based on what we have seen in the lab. If the results satisfy us, then it may be worth keeping. But if we would like to push further, then the first round of learnings will give us enough insights to actually iterate for the next round as well. And I put steps actually, but I want to mention or highlight one single thing here, which is the mutation. I know I have talked and mentioned this over and over again, but mutation should should be the strategy to follow only after reviewing and properly experimenting with the construct design so that you can know that there is no other way around resolving the target that you are trying to work on in the lab. And today we are in a very good position to actually actively work on it because in 2000s, one construct sometimes may have costed up to $18,000. But today with larger panels, we can actually execute on them in a significantly more cost-effective way that would allow us to run multiple of those panels to have a good screening and have a good candidate pool before we lock in a decision and proceed with the next step. And putting all together, construct engineering is a big low risk lever when we actually start doing discovery around that. The second one is yield, doesn't mean developability. A lot of protein doesn't mean a good amount of well-behaved protein, where the prioritization should depend on the goal of the experiment. And because of that, we have to first decide on what we want to achieve as part of an experiment campaign. And then we should start strategize around that and as determine the construct, host, and the metric we are optimizing for. And last thing, literature tells us what work, but it shouldn't define the edge or the limits of the design space that you're working on. And that is it. Thank you very much for listening.
Jalar, thank you. Great presentation. We really appreciate it today. I would like to ask the audience to please type some really good questions into the chat box before we close. I know we're finishing a little bit early today, so we have plenty of time for questions. I think I can go ahead and start while y'all are thinking about some good questions. Chalar, I'm sure you mentioned this, but I just want to clarify the power of your AI model just based upon my time way back when I was in the lab. I remember I used to do a lot of site-directed, like what we called scanning mutagenesis of like my favorite transcription factors. And I would look for mutations that either enhanced transcriptional activity or maybe repressed it or enhanced the transcriptional repression properties of that transcription factor. So your AI platform allows for like I guess, a better selection of the mutations to achieve like the final output of the function of the protein, or does it enhance the ability to make the constructs more efficiently, I guess? Can you clarify a little bit more about what your platform does?
Of course, thank you for the question, Rob. Our platform can actually support both things, but we are separating them from each other because we think they serve two different distinct needs. For mutations, our model can discover or optimize for thermostability while keeping the fold similar to the original target. So we
Mhm.
are screening or allowing scientists to run campaigns, such as alanine screening, for example, to give them a ranked set of mutations based on the goal of thermostability or solubility, while ensuring that the structure or the fold of the original target and the mutated target are similar to each other. So when it goes to the lab, the function or all the downstream assays that they may want to run would behave the same way as the original target. So it's
Mhm.
about discovering the right point mutations for
Mhm.
for evaluating a binder or evaluating the original targets in whatever experimental use case that you may have. And with
Mhm.
regards to yield and developability, we have our design module that supports that. And again, our strength is coming from allowing scientists to rank different constructs of the same target in a certain expression host, where our models are very capable of ranking which construct would lead to higher yield or higher developability against the other ones. Coming up
Okay.
with specific yield or specific numbers that you may observe in the wet lab is extremely challenging because we know even the noise range of the same experiment between two different labs in the world is extremely large. For a machine to come up with exact and accurate results is very challenging as well,
Mhm.
which is why we are always highlighting the ranking power rather than specifically telling how better a construct will be against the other one.
Okay, great. Thank you for that explanation. It's very clear now. And while I'm still waiting on questions from the audience, let me just ask you a little bit about your business model. Once again, please forgive me if I missed this, but do you contract out your services to like pharma, biopharma, biotech, and maybe even academic researchers for proof of concept, and then maybe they test in their own wet labs, or do you also confirm the output in your wet labs? Like, what's your business model, and can you even reveal some big clients that you have that's publicly known?
I can mention about our business model. We are working or following a software as a service business model where we are licensing our software with a subscription fee to our clients. But we know there is a lot of question mark about AI in the field, which is coming from, I will say, experience that scientists have built over the last couple of years, which is why we always offer a paid pilot to make sure that our prospects can experience the product on their existing data sets to see how well the ranking is at a discounted price. We
Mhm.
don't own a wet lab, but we have multiple CRO partners that we are continuously running experiments on to both improve our models and also to showcase the ranking power and the capabilities of our platform.
Mhm. Fantastic. Great. Software as a service subscription model. I think it's a fantastic business model, especially based upon your platform. So it's very exciting. I will tell you, we didn't get any questions from the audience, so I guess we'll go ahead and wrap up a few minutes early. I will tell you that we had good attendance today. A lot of folks from around the world, some specific areas, of course, Houston, other areas of the United States, of course, Berlin, where Orbion is based, and then even Cameroon. So we had lots of good folks from around the world. I want to thank our attendees for joining us today. Certainly, Chalar, I want to thank you as a speaker. It's fantastic technology, very interesting what you and your colleagues have accomplished. I want to congratulate you and the team at Orbion. And then I want to thank my colleague, Natalie Cow, for executing another flawless webinar. Natalie, you did a great job with it. So thanks to everybody. And Chalar, we really appreciate your efforts today.
Thank you very much for hosting, Rob.
You're welcome. And with that, we'll sign off. We'll say good afternoon, good evening, good night to everybody. And that concludes our webinar for the day. Thank you and goodbye.